Hey everyone, this is the first episode in a series of the most useful college courses for a game developer. Today let's talk about algebra. Let's start with the most popular use of algebra, namely vectors. What is a vector? In mathematics, a vector is any object that has two properties. The first is direction. The direction of a vector is like a compass pointing the way, such as northeast or southwest. It shows where the vector is aimed, just like when you point and say, over there, that's a direction. In summary, the vector's direction shows us which way it points. The second is a magnitude. We can see that this vector has magnitude equal to 5. Also, we can see that this vector has a northeast direction. Our vector is usually an arrow embedded in the coordinate system, so let's spend some time on it. As we can see, our coordinate system have two arrows. One that is blue is called y-axis, and second one that is red is called x-axis. We have an arrow that starts at point A and ends at point B, so basically we created our first vector. We can calculate our vector AB by subtracting the coordinates of the starting point from the ending point. As you can see, subtracting the corresponding coordinates, we got the result of 2, 3. We can represent our result as a movement in space. Look at our dashed line in the figure. We moved 2 units to the right and 3 units up. If you wonder if the order matters, take a look. Subtracting in reverse order, we get the opposite vector. This is very useful information when we debug our code. We can create an opposite vector by swapping the sign of each coordinate. This way, we get a vector of the same length but with opposite direction. We will talk about operations on vector, starting with basic operations. The first is the additions of vectors. Geometrically, we can interpret this as follows. The sum of vector A and B is vector C, which starts with the beginning of vector A and ends at the end of vector B. Numerically, it is represented as addition of the corresponding coordinates. Subtraction is basically the same as addition, but vector C ends up at the end of the inverse of vector B. Numerically, we can add to vector A inverse of the vector B, like with addition, or we can subtract from A vector B. Let's stop for a moment and talk about the applications of the knowledge we have learned. In League of Legends, to calculate how to launch a projectile, it is necessary to use a vector to specify the direction in which our projectile will fly. We know the position of our player, point A. We also know the position towards which our projectile is to fly, point B. We can create an AB vector by subtracting the coordinates of the points, so we will know the vector that specifies the direction of our projectile. In this case, our vector AB is equal to 1, 1. Another application of our vectors is character movement. Movement is basically moving our character by a small distance every frame. In this case, the position of our character is P, and by clicking S on the keyboard, every frame we add a vector v to P. To each key on the keyboard, we can assign a vector that corresponds to it. So by clicking the corresponding key, we will go in the right direction. Let's continue with our basic operations. It's time for vector multiplication. We can only multiply a vector by a number. Geometrically, this is represented as copying and pasting as many vectors as we have multiplied. Algebraically, it is the same as multiplying by a parenthesis. Each coordinate is multiplied by a number. Dividing is practically the same as multiplying, but in reverse. Instead of copying and pasting, for example twice, we divide the vector into two equal parts and take one part as our new vector. Algebraically, it is dividing each coordinate by a number, exactly like with parentheses. Next up is magnitude. I created a sample vector. As you can see, I have marked with dashed lines that we go to the right by 2 units and up by 3 units. The sketched lines form a right triangle. Using
Pythagoras' theorem,
we can easily calculate the length of our vector. In general, we can for each dimension apply the
Pythagoras' theorem.
For example, for the perpendicular, and this is how we will create a general formula. Now it's time for the unit vectors. A unit vector is any vector in space of magnitude 1. It doesn't matter at which point the vector begins and what angle it has, as long as the magnitude is equal to 1. When we draw a circle with a radius of 1, we are able to draw infinitely many units vector that start at the center of the circle and end at its edge. We can easily convert any vector into a unit vector. Here we have an example vector, 8, 6, whose magnitude we can easily calculate from
Pythagoras' theorem.
Dividing each of its coordinate by calculated magnitude, we get a unit vector. Unit vectors are essential for character movement. If we hold down both W and D keys to move upright, the movement vector is 1, 1. Its length is the square root of 2, which means we will move faster than when we moving only right or only up. Because of this, before moving or performing additional calculation, we need to normalize our displacement vector. Now we are going with complex operations. First is dot product. The dot product is an operation that results in a number. This operation has two equations. The first, which involves multiplying the corresponding coordinates and adding them, and the second, which involves multiplying the magnitude of the vectors by the cosine of the angle between them. Using the dot product, we can simply calculate the value of our angle. Take a look. Firstly, I calculate using first formula, then I try to calculate using second formula. At the very end, I can compare the results of two equations. And we got that cosine theta must be equal to 0. We can read this value from trigonometric tables, so we know that our angle theta is equal to 90 degrees. The dot product has many uses. The first that comes to mind is determining if an enemy is within the field of view of, for example, a turret with a specific cone of vision. To begin with, I will draw the turret's range of vision. Within this range, our turret will shoot at any enemy. In green, I will mark the forward vector of this turret. Between the forward vector and the end of our range of vision, there is some known angle, suppose 45 degrees. To know whether the turret should fire a shot, we need to draw a vector from the turret to the enemy. The angle between this vector and the forward vector must be less than or equal to 45 degrees. We can label our forward vector as A and assume that it is equal to 0 minus 1. We will label the vector from the turret to the enemy as B and assume that it is equal to the value I am just drawing. Now I will calculate the dot product of our vectors. They are already normalized, so it is simply cosine of theta. Using the second equation for the dot product, I found that it is equal to the square root of 2 divided by 2. By comparing the two dot products, we find that cosine of theta is equal to the square root of 2 divided by 2. From the trigonometric ratios table, this shows that theta is 45 degrees. From these calculations, we know that the angle between the turret's forward vector and the enemy is 45 degrees, which is exactly within the turret's vision range, so it will start shooting at the enemy. Second advanced operation is cross product. Cross product is very similar to dot product, but a little bit reversed. Take a look. The result of the cross product is a vector that is perpendicular to our two vectors that we use for this operation. It is worth mentioning that we use cross product only for three-dimensional vectors. I marked our perpendicular vector that I called A cross B using green color. When we take our vectors A and B, copy them and create a parallelogram from them, we will find that its area will be equal to magnitude of our vector A cross B. Using cross product, we can create perpendicular vector to every shape that we can draw. Check this surface. In blue are marked vectors perpendicular to each face of this plane. Such vectors are normal vectors. Like for the dot product, there are two equations for the cross product. The first involves multiplying the magnitude of vector A with the magnitude of vector B, the sign of the angle between them, and vector n. Vector n is perpendicular unit vector. As you might think, very rarely we know the perpendicular unit vector, that's why we also have the second equation. Our second equation involves multiplying the corresponding vector coordinates with each other and subtracting them. Unfortunately, we need knowledge of the matrix to derive them, so we will get to that in a later chapter. For example, I have written out the calculation of the cross product of vector A and B here, which gives us the perpendicular vector C. I found a very nice visualization that shows us the relationship between the cross product and the angle. As you can see, the larger the sign is, the longer our result vector is. Also, with cross product, we can check the orientation of two vectors relative to each other. We need to place our hand in such a way that the index finger points towards the first vector, in our case the red vector A, and the middle finger towards the second, in this example blue vector B. Then the thumb will be our cross product results, and hence we know whether the results vector points up or down. Additionally, we see that in this arrangement, if the cross product points up, vector A is on the right side of vector B, and when it points down, vector A is on the left side of vector B. With all the knowledge learned in this video, we are able to count the reflection of a grenade of a wall in the same way as in Counter-Strike. First, I will draw the two known vectors A and B, which form the wall from which our grenade bounces. Also, in green, I will draw the normal vector C of our wall. I draw our wall from the side in 2D to simplify calculations. We can calculate the normal vector C using cross product. The normal vector C is useless to us. We need to normalize it first. I will now draw our normalized vector n in the figure. I will mark the vector v, which represents the grenade's flight path, in red. We are looking for the vector that represents the reflection of the grenade off the wall, which I will mark as the yellow vector d. First, I will extend the vector v. Next, I will draw the orange vector e, which is the projection of vector v onto the unit normal vector n. Finally, I will reflect vector e and extend it as well. Now it's clear how we can obtain our vector d. Using the geometric definition of subtraction, we see that vector d is equal to v minus 2e. The biggest question is, where do we get vector e from? I didn't mention it earlier because I wanted to show it in context, but the dot product easily allows us to project a vector onto another vector which is normal using this formula. Once we have calculated vector e, we just need to substitute the orange formula into the yellow one and we will get our final equation for calculating the reflection. Congratulations! After watching this video, you, the viewer, have acquired the essential knowledge about vectors, bringing you one step closer to writing your own game.